So I will be talking about greenhouse gases and air pollution as seen by satellites. So I will now focus on kind of a very narrow viewpoint to the Earth by observing the Earth with one observation methodology here. And I will start with this type of an image, which shows you the air pollution, and in this case nitrogen dioxide, global concentrations. These are average values over year 2018, and these have been measured with the like a best satellite what we have at the moment for air pollution monitoring. From this image, you of course focus on the red areas where there are most nitrogen dioxide in the atmosphere. You see the areas with a high population. Nitrogen dioxide is emitted to the atmosphere from combustion processes, and traffic is one big source also. So it's where people are, where there is industry and so on, where you see the high elevated nitrogen dioxide values there. But then you see also cities, clearly, and in different places of Earth you probably have your favorite places, what you are now looking at. And you can also see with these lines here over the ocean. So this is the ship emissions of nitrogen dioxide, which can be seen all the way to the space with the satellites. So there is no modeling here, it's all data, average data. With the satellite observations, it's typical this type of observations to also average the data to get rid of noise and other unwanted effects there. So we typically have some yearly averages, monthly averages, but in some cases also one satellite overpass data can be analyzed and seen different things. In this particular satellite, it has a very wide view what it sees at one time, and it means that during one day it can actually measure the whole globe. All right. I will then say a few words how that type of satellites are making their observations. So for measuring air pollution and greenhouse gases, optical instruments are favorable, and they typically use sunlight as the source for the observations. So they measure what the sunlight when it's reflected back to the satellite from the Earth's surface and the atmosphere. Of course, you can then understand that if there is no sun, there are no observations, so we have a gap in the observations on the nighttime. We can only measure in the daytime, but also clouds then hamper the measurements. Very, very heavy aerosols can also be then complicate the data analysis. And what the satellite then measures is a spectrum. Here with the optical, in this example, it's from UV wavelengths to the near infrared wavelengths, where all the gases in the atmosphere have left their finger marks. And you can see in different places there are different gases that have different features in this spectrum left there. And this can be used to calculate how much there has been each of these gases in the atmospheric column which the satellite has seen. So typically the satellite observations, they represent some type of a column or then partial column of the observation. And there is also like a spectral or spatial resolution that the satellite covers, which is typically of the order of a few kilometers in these atmospheric composition observations. Then I continue more to show you some pictures of the data. So here is observations from a satellite that was already launched almost 20 years ago, which means that we can really see changes in the global air pollution. In this case, it's still the nitrogen dioxide, which is probably the most mature of the parameters that we can measure from space. This particular satellite instrument, OMI, was built in 1990s and early 2000 in the Netherlands and in Finland. And it was launched in the NASA Aura satellite, and it's still operating. Here we see the global situation in 2005 in nitrogen dioxide concentration. You see high values in Asia, Europe, North America. But then if I go forward in time, so 2010, and a little bit perhaps go back and forth, it works, yes. You see the changes. You see that in Europe and in US, the pollution has reduced, while in Asia, it has increased in these 5 years that I show here. Then if I go further on in time to 19, you see that now also China has started to reduce, so they put on a very strong emission regulations there, and it has also reduced the nitrogen dioxide concentration in the atmosphere, while in India it has increased in this case. So this type of things one can study in a global frame also when we have a long, consistent data sets, and what is important here is that they are all measured in everywhere in the world with the same instrument. Something about Finland, which was very, very blue in the previous image, but of course by zooming in and changing the color scale, we see also things in Finland. This is actually with the other satellite now. We see the effects of the COVID-19 restrictions in people did not use cars to go to work, etc. The traffic was reduced. So comparison between the years to 2019 and 2020, 2 months in April and May in both years. And you see clearly that there is a much reduced nitrogen dioxide concentrations in southern Finland in 2020. The reduction was about 40%, and this corresponds quite well with the surface ground-based observations as well. And then I come to the very, very important part, that when we interpret the satellite observations, which are by nature non-direct observations, we need data processing, solving mathematical, computational, statistical inverse problems to derive the concentrations. It is important part that we also compare how our observations correspond to ground-based reference observations and try to understand the uncertainties there. So in this case here, we compare different types of ground-based observations with the satellite observations, and in this plot they have been plotted according to the weekday, so that you see the variability in Helsinki area on the nitrogen dioxide along the days. So less in Saturday and Sunday in the weekend, but more in the weekdays. And here in this picture, the satellite is in in yellowish color, and then the ground reference, which is a similar observation type, but from surface towards sun, is blue, this Pandora instrument, and then we have air quality station observations, which is shown with this purple color here, which is of course measuring very, very different thing on surface level, while the others are measuring column. This curve here they have been scaled so that they are comparable. But of course, when validating the satellite reference observations, it's really important to be able to, as well as possible, make similar observations and ensure that everything is correct. Then I jump to another constituent. This is sulfur dioxide, which is another air pollution constituent. Also has natural sources in volcanoes, but then a lot, or the largest sources are often related to mining industry, smelters also. And here in the global map, we see this is a global situation in 2016, and here you see this is like a yearly average, and there you see clearly the largest point source, which is Norilsk in Russia. Here is another satellite image of the same site, but this is like 1 day image, so it shows up, I would say, every day in the satellite pictures. This is Orjansk. It's such a big source. So we can also obtain observations in areas where it's not so easy to get other types of measurements. And in particular, these geopolitical situation observations over the large areas of Russia are, of course, very important for environmental studies. Then I go to a specific case study. This is a verification of emission reductions, and this was a Finnish company who implemented a device to capture sulfur dioxide emissions in Namibia. So I go to Africa now. They implemented it 2015. So this is what we see with the satellite in sulfur dioxide 2014 in Tsumeb, Namibia. We see highly elevated values there. This is 2016, and there we don't see anymore such clearly this site. Here is actually then emissions calculated from the satellite data with the solid blue curve and compared to the reported site with this dashed blue curve. And you see that there is similar features. They are not identical, but there are very similar features after this. This is 14, where there was the maximum emissions estimated, with then the coming years 15 and 16. So clearly we can verify with a satellite then what the companies report, that they have reduced the emissions. So it can be useful in this sense, so in sense of independent verification. Some other gases and features. What is important, of course, we know increased fires in many places in the world. Now this image is about Canada and the record-breaking fire season actually taking place this year there. Here are a time series of fire counts as seen by the satellites, and there you see clearly that it's going to 50,000 fires in Canada compared to the previous years where it has been closer or lower than 10,000 fires per year, or per month. These are monthly fires. And here just animations of these are daily pictures of so-called aerosol index, which is like a measure of highly elevated or high in the atmosphere traveling aerosols in the atmosphere. So in like a 1 week time period. See how the aerosols, so small particles from the fires, travel in the atmosphere. These are from the Canadian forest fires. Then I go to greenhouse gases and the satellite observations of carbon dioxide. I have to say first that the carbon dioxide observations with the satellites are not as mature as some of these air pollution parameters like the nitrogen dioxide and sulfur dioxide, which I just showed. So the methodology to measure them is not as mature. And in addition, there is a difficulty that the source is not so easily identifiable in this data set because the gases are long-lived in the atmosphere. And that's what we can, or I try to here quickly demonstrate. So here are anyway satellite observations of carbon dioxide. We still have a lot of observations from 2014 onwards. Specifically with a NASA satellite, you see the increasing, globally increasing carbon dioxide values with the satellite. So there are in 1 month about 2 million observations with a satellite of carbon dioxide as well. This data is typically combined with an atmospheric transport model to derive the emission sources and sinks. And that is an important step, not straightforward step, but there has been now first attempt to derive really the global carbon fluxes over 100 countries that have been estimated in a recent publication that came out earlier this year. And that's shown in this top image. So here the countries on yearly level that are emitting more are shown with these brownish colors, while the sinks are more greenish colors. So this is now based on using the satellite data and the atmospheric modeling to derive this type of, it's called top-down emission estimation. And the results here are, as you notice, they are different than the reported inventories-based estimates of the carbon sinks and sources, which are referred to as bottom-up, which model the behavior and consumption of fossil fuels, etc. So calculational values. And there are differences, and it is, of course, very, very important now to understand the differences and also then to bridge the gap between the understanding of these two approaches. I here added in bottom another picture of satellite observations. So this one does not count for modeling at all. So this is only a carbon dioxide anomaly based on the satellite data. So basically this has been estimated like the anomaly compared to the local background, so highlighting areas where there is a more carbon dioxide compared to the background. And here you see anyway that there are some similarities between these two maps. What we are looking for a lot in the satellite community and hopefully for the rest of the society as well is a new satellite, CO2M, to improve the present carbon dioxide observations so that we can improve also the estimation techniques that can then be used to support the climate actions and the Paris Agreement, and also verifying the inventories. I also show quickly here one example of the satellite capabilities. This is a case where we can identify emissions which are not included in these inventories or which are not reported. And this is in Russia, Sakha Republic, Siberia area, a sort of area where there is a lot of oil and gas industry, and here we see with the satellites methane emissions from this Talakan site in this lower picture. This is using an average data of actually 3 years in this case. But it's important to understand that, for example, this source is not included in the carbon inventories. And as a summary, I would like to highlight a few topics. So satellites can monitor air pollution and greenhouse gases globally, and they include areas which cannot be measured with other techniques so easily. I think what is important is that in future and already now, so the analysis methods are developing fast, and there is a huge potential and huge need for all types of data fusion technologies to combine and use all this data that exists. And I think the AI methods are also promising there. Ground-based reference observations are extremely important, as I already mentioned. What I did not mention yet is that these satellite data sets from the European Space Agency and from, for example, US satellite organizations, it's free, the data is free and open for everybody to use. And last most important part is here, and I see my time is running up. So I think that satellites can really be useful in supporting the climate mitigation and adaptation. So these long and consistent time series allow studying trends and changes globally, and they can report or reveal unreported emission satellites. And I think that in this top-down, bottom-up framework and discussion, we will learn a lot more and new things about the carbon emissions and sinks globally, and support in that way also the Paris Agreement process. Thank you.